In this video, we're going to learn about electron configurations in an atom. So an electron configuration is simply a way to represent how your electrons are put into the different subshells and orbitals of an atom. And so some background information you might need before doing this lesson is information about the different types of subshells there are and different types of orbitals and how many electrons they can each hold. For example, an s orbital within the s subshell can hold 2 electrons max. Same thing with a p orbital within an s subshell, and same thing with the d orbital. They can each hold 2 electrons max, but the thing is, these orbitals are found within subshells. So this is the box that's only one box. This is 3 boxes. There's 3 sort of different boxes of p, so that means you could have a total of 6 here. This one's only 2. This one here was the boxes where there were 5 boxes in them. 1, 2, 3, 4, 5. So you could hold a max of 10 electrons. And this one here was the one that was made up of 7 boxes. So 1, 2, 3, 4, 5, 6. And you could hold 14 electrons there. So that background information is good to know. If you don't know too much about that, please make sure you go back to watch previous videos and review lessons to understand those concepts. So to write electron configurations, to write where the electrons are within subshells, and to have some idea of how to fill them up, like where do I put them? Do I put them in the S first, and the P first, and the D first? We need to look at a few rules. One of the first rules for creating an electron configuration is the Offbow Principle. And this principle basically means that when you add electrons to the subshells and to the orbitals, you always want to add them to the lowest orbital available first. So you always want to go from lowest to highest in terms of energy. And this principle really means to build up. So when you build, start from the bottom and then make your way up to build up. So how do we know how much energy is found within the orbitals? Well, let's go take a look at this energy level diagram over here. This is a diagram that shows the energy found within the electrons at various shells and subshells. So as you go up, the energy goes up. You'll notice that shell 1 has the lowest, then shell 2 is higher, 3 higher, 4 higher, 5 higher, 6 higher, so on and so forth. So as you can see, this energy is related to the distance from the nucleus. The nucleus would be about over here, let's just say. And the farther you get away from the nucleus, the higher your energy is, because you're not tied down to the nucleus. You don't experience that same pull or attractive force from the protons. Also, there's a lot of electrons in between that are repelling the outer electrons as well. So the one with the lowest energy is really the n is equal to 1 because it's very, very close to the nucleus. And then as you go higher and higher, you have more and more energy as you move away from that nucleus. So if you look at the shells, though, the shells increase in that order. You'll see within the shells you have your subshells, like you have your S, for example, your 2s, your 2p, 3s, 3p. In general, this is the order you'll see for the energy. 1s is lowest, then 2s, and within that second energy level, the 2p is actually higher in energy. So what this basically means is, according to the Offbow Principle, when you're putting in electrons, start with the 1s. Once that is full, go to the 2s, then go to the 2p, then go to the 3s, then the 3p. Then it gets a bit weird here. You would think you would go to the 3d next, but you don't. You actually go to the 4s, because even though the 4s is higher in terms of a shell or energy level, the 4s is still lower in energy than the 3d. And that relates to the repulsive and attractive forces between electrons and the nuclei and all the electrons you have there. But it's something that you just need to remember for now, that we have our 4s being lower in energy than the 3d. So you'd actually fill the 4s first. And this, if you had to use this diagram to remember those different energy levels, it gets a bit confusing. So there's one trick that you can use to remember the order of energy, and it's this trick over here. You can draw yourself a diagram like this here. And in this diagram, what you do is you, in one column, put all your S's, in the other column, put your P's, in the other, your D's, and the other there, your F's. And so you have 1s to 7s, then 2p because there's no 1p, right? 2p to 7p, then 3d because there's no 2 or 1, to 7d, and then 4f because there's no 3, 2, 1, all the way to 7f. And this is the filling order. So you start by doing your 1s first, then diagonally up, this is your 2s, and then your 2p and your 3s, and then your 3p and 4s, and then your 3d and 4p and 5s, and then your 4d, 5p, and 6s, and then your 4f, 5d, 6p, 7s, and then your 5f6d7p, and then your 6f7d, and then your 7f. And so this is the order to fill up the orbitals within an energy level diagram or electron configuration based on the energy levels of the orbitals. So if you draw this out on a cue card and you have it next to you when you're doing some homework, it'll make your lives a lot easier, especially when we start doing some examples of electron configuration. Now, when we're trying to make electron configurations, there are two other rules we need to follow. The other rule is called Pauli exclusion principle, and what that means is only two electrons can occupy an orbital, and they must have the same, they must have opposite spins. So that's where if you have a box like this, you can only fit two electrons in there, and they have to have opposite spins. They can't have the same quantum numbers. So every electron has to have a unique set of quantum numbers. They can't be the same for two electrons, otherwise they're the same electron. That doesn't make sense. So this is sort of where the different ms values come from. This one's plus 1/2, and this one's negative 1/2. The other rule to follow is something called Hund's rule. So I'm going to show you what Hund's rule is. We're going to read it out here, and then we're going to try to try to do it. So you have to visualize Hund's rule as opposed to just understand it, or it's hard to understand just from the statement. So single electrons with the same spin must occupy each equal energy orbital, or each orientation, before additional electrons with opposite spins can occupy the same orbital. So I'm going to fill out these subshells here, the p subshells, the correct way and the wrong way to show you how Hund's rule is applied. So let's say I want to put 4 electrons into a p orbital. I'm going to show you the wrong way first. If you do this, 1, 2, 3, 4, this is wrong. The reason is there's too much repulsion here and here by pairing them right away. You don't want to pair them right away. What you do is you want to start by placing them singly. Up, then go to the next one, up, the next one up, and then go back and pair like that with the opposite spin. It's almost like when you were doing Bohr-Rutherford diagrams, you would do 1, 2, 3, 4, and then pair. So it's the same idea over here. So this is the correct way to do it. That's called Hund's rule. This is based on the stability of the atom. We want to draw the most stable configuration. And so the most stable is where you minimize repulsions by placing them singly first and then going to pair with the opposite spin after. And again, that is called Hund's rule. So now what we're going to do is we're going to go take a look at how do we apply these different rules to make an electron configuration for an atom. So the guidelines are over here. We want to place orbitals. We want to place electrons into orbitals based on increasing energy levels, so from smallest to biggest. And as we saw earlier, that was the Offbow Principle. You want to completely fill the orbitals of the same energy level before adding any to the next. So always make sure you filled your orbital that you're working in before you go on to the next one. Make sure that each orientation of an orbital of the same energy level receives an electron before they are paired, and make sure that those have the same spin. So in other words, this is Hund's rule. Place singly first and then start pairing after. So these are both aspects of Hund's rule. So let's go take a look and try a simple example. We'll do oxygen first. So I'm going to build an energy level diagram for oxygen. You do need to know how to draw something like this. You put your energy on your label here. The arrow needs to point up to show your increasing energy. And then these are the correct order for the energies of the different orbitals and subshells. So we have our oxygen from our periodic table. That's atomic mass of 16 and symbol O and atomic number 8. So that means we have 8 electrons to place. So we'll start placing our 8 electrons in this energy level diagram here, starting from the lowest energy, one at a time, first the up, then the bottom. That's full. Now we go to 2s, first the up, then pointing down. And we only have 4 more to place because we've already placed 4. Now we have to go to the 2p. Place them singly first, 1, 2, 3, and then pair with opposite spins, 4. So we've drawn our electrons for oxygen in an energy level diagram. An energy level diagram What is that? So let's call it energy level diagram. Level diagram. Definition. It is just a visual representation. Visual representation of electrons in their orbitals, and that follows the rules such as Offbow, Pauli exclusion principle, and Hund's rule. So from this, we can make an electron configuration. I'll show you a couple different ways to make an electron configuration. So we're going to do an electron configuration for oxygen. We'll do what's called a complete configuration first, and then a shorthand. So the parts of the configuration will look like this. This is not related to oxygen. This is just an arbitrary example. The big number at the front indicates the energy level you're in. So this is the energy level 3. This represents which subshell and then orbital you're in. So subshell P, you're in a p orbital. And then this number here represents how many electrons are in there. So in that particular p subshell, you have 5 electrons in there. So we're going to write essentially what did we draw in this diagram here, just as a series of numbers and letters to represent that. So in our first subshell orbital, we have 1s, and we have 2 electrons in there, the 2 arrows. In our second one, we have 2s, and we have 2 electrons in there. And then over here, we have our 2p. How many electrons do we have there? Well, we have 1, 2, 3, 4. 4 in there. So this is the electron configuration, the complete electron configuration for oxygen. There are 2 other ways you could have done this. I'm going to show you those 2 other ways. The first is by using this diagram here. Oxygen has 8 electrons. So I want to place the 8 electrons according to this diagram. So in the 1s, I'll place 2 electrons. In the 2s, I'll place 2 more because that's all you can fit, 2 electrons per s. For P, you can fit 6 total, for D, 10 total, and for F, 14 total. I have 4 electrons left to place. I'm going to go put them in my 2P here. I don't need to put 6. I just have 4 left to place, so I can put 4 electrons there. So what did I do? I put 2 in the 1s2, 2 in the 2s2, 2 in the 2s, and then 4 in the 2p. So 1s2, 2s2, 4p4. Very quickly, using this method again, let's say I was doing neon. Neon has 10 electrons. So for neon, what I would do is, similar approach, 2 electrons, 2 electrons. That's 4 so far. Let's do actually something with 11 electrons. I want to show that. Let's do sodium. Sodium is 11 electrons. Okay. This will be a better example to show. So 2, 2, that's 4. In 2p, I can fit 6 total. So I'm at 10. Next, I'm going to 3s. But I can only have 1 left, so 1 there. So this would be 1s2, 2s2, 2p6, 3s1. And that's essentially how I'm filling in my electrons into the respective orbitals when I'm making an electron configuration or energy level diagram. That would be for sodium. So that's another way to do electron configurations, is to use this sort of chart over here. Another way you can do it is by looking at our periodic table. This is probably the most efficient way to do electron configurations using the periodic table of elements. So what you need to notice is that the periodic table of elements is actually organized according to what's being filled up. In our first period, our 1s is being filled up. So by the time you get to here, you basically have 1s2 to this point here, 1s2. That's helium. Then once you're past that, we have our 2s being filled up. So 2s1, 2s2. And then over here, if you keep going in that period, in period 2, you have 2p1, 2p2, 2p3, 2p4, 2p5, 2p6 over here. So by the time you get to the end here, you have 2p6. Then if you continue into the third period, you have 3s1, 3s2, then 3p1 all the way to 3p6, so 3p6 by the end over here. Then fourth period, you're filling in your 4s1, 4s2. Now, before you can go to your 4p, you have to do your 3d first. So from here to all the way to the end of this transition area here, you get 3d10. And then we can go into 4p1 all the way to 4p6. And then from there we go to 5s, 1, 2, and then 4d10 at the very end. 4d10. And then 5p1 to 5p6 here. And then we get to our 6s, 6s1, 6s2. Before you can go to the 5d10 over here, you need to do the 4f's down here. That's for the row 6. So then you get 4f all the way to 4f14. And then you could go to 5d10. And then after 5d10, you can do your 6p6. Then you have your 7s2. Before you can go to 6ds, you have to go to 5f14. And then periodic table continues, but you could essentially go all the way up to here, which would be your 6d10. And then if you continue going, you'd reach a 7p6. And that's what you can see from our diagram. Over here, we have 7p6 there. And you could theoretically continue if you excite your electrons and go into higher energy levels as needed. But you could use your periodic table to find the electron configuration instead. So let's see what that would look like for oxygen. So here's oxygen. Oxygen, let's go to our periodic table that you're allowed to use on an assessment. So we can go up here, open up a periodic table, and I'm just going to download it so we can draw on it. Here is oxygen. And what we're going to do is we're going to make our way through the periodic table, filling out the electron configuration as we make our way to oxygen. So this first period is 1s1, 1s2. So that's filled up. Let's continue. Second period, 2s1, 2s2. That's filled up. Now we're going to go here, 2p1, 2p2, 2p3, 2p4. That's filled up. Let's do fluorine. If we're doing fluorine, similar idea. Very similar to oxygen, right? 1s1, 2s2. So 2s1, sorry. Actually, that's not 2s1 at all. We're still in 1s1. So 1s2, I should say. 1s2. Now here we're at 2s1, 2s2. So 2s2. Then 2p1, 2, 3, 4, 5 for fluorine. And so we simply use our location in the periodic table and our knowledge of which blocks are being filled up to find the electron configuration. We'll do another one. We'll do bromine. Bromine's a bit of a busier one to do. Let's go ahead and try it out. So bromine is over here. So we have 1s1, 1s2. Okay, 1s2 is filled out. We have 2s1, 2s2, and then this over here goes all the way to 2p6, right? 2p1, 2, 3, 4, 5, 6. So 2s2, 2p6, then 3s1, 3s2. And then over here we have 3p1, 2, 3, 4, 5, 6. 3p6. And then here we have 4s1, 4s2. Now we get to the 3ds. So 3d1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3d10. And then 1, 2, 3, 4, 5. 4p5. You could rearrange it to write it like this. 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p5 with your highest shells here. but this is the correct filling order here. So you can only rearrange really after you've filled it out with the correct order, and then you're okay. It means the same thing in the end. Both would be acceptable as long as you started with the correct filling order. And what you might notice is that your highest energy levels here, these are your valence electrons, the 4s2 and 4p5. And bromine just needs one more to get a full valence shell, so a 4p6, and that would be a full valence shell for bromine. We'll talk more about that later on. So that's how you would use your periodic table to fill in the electron configuration for bromine. This is a complete configuration. So is this, and so is this. You can actually do a short form of the configuration, which makes your lives a little bit easier. The short form of the configuration is right over here. It's also called the noble gas configuration. The noble gas configuration. It's a shorthand way of writing your electron configuration for an element. So what you do is, let's just take a look at something like let's say bromine. We look at the noble gas that comes before it, and that's argon. So you look at the noble gas that comes before it, that's argon. And what I want you to get is, let's go back to our periodic table here. Argon, its electron configuration is this all the way up to 3p6, right? Because this is the third period, 3p6, right here. You usually choose the highest energy level with a full p, and that's the end of the noble gas that came before your element. So all this is argon. So instead of having to write all that out for bromine, what you could do is you could simply say, let's replace that bit by argon. And then afterwards, write the rest of the configuration. So you write argon like that in square brackets. And then after that, you can say 4s2, 3d10, and then 4p5. And that's a noble gas configuration for bromine. It makes your life a lot easier, so you don't have to go and do the entire configuration for the element over and over and over again. Let's try a quick example for iodine. So if I was doing a noble gas configuration for iodine, here's iodine right here. The noble gas that comes before it is krypton. So I can simply do krypton and then continue from there. So this is period 5 right here, right? So that means this is my 5s2. And then afterwards we have, so 3 was over here, 3d was over here. So 4d is here. So all the way to 4d10. And then we have, since that was 5s, this is 5p. So 5p1, 2, 3, 4, 5. 5p5. And that would be the shorthand notation or the noble gas notation for iodine. So I didn't have to write all the way up to krypton. I saved a lot of space by just putting krypton there. And then I put in the remaining electrons that need to be put in for the noble gas, the rest of the noble gas configuration. So that was just some examples of electron configurations for different elements using the periodic table technique. We also saw the technique using the chart over here, which you could memorize, or you could just draw out in a cue card and use that. And the more you use it, the easier it'll become to memorize. And really, it's worth spending some time learning how to memorize the periodic table over here and how it's ordered. We'll just finish up by doing the electron configuration, the noble gas one for oxygen. If you look at it carefully, this is kind of one of the weird ones. The noble gas before oxygen is right here. That's helium, and that's only 1s2. So it's our filled S shell there. And so to do that, we just replace the 1s2 with helium, and then we put 2s2, 2p4. And that would be the noble gas configuration for oxygen. It doesn't save us much time because oxygen is not very long anyways. In the next video, we're going to take up the 2 questions that are over here, manganese, some energy level diagrams, and then aluminum as well. Make sure you try them yourself and then check your work afterwards in the next video.